already we have seen the AW questions of estimation costing as well as the surveying area. Now we are going to deal with the questions of transportation engineering. Okay. Now let us see the questions that were in the AWA exam for this transportation engineering. The very first question comes here. The coefficient of average rolling friction of the road is R. Its grade is G%. If the grade of the road is doubled, what will be the change in the braking distance for a design vehicle to come to stop measured along the horizontal, assuming all other parameters are unchanged? Dash. Actually, this is the GATE 2019 question. Same to same question was copied here. It was pasted here. 19 question actually this is 19 marks question actually this is. Same question was copied here. Of course, almost all the questions, that means the bigger numerical questions, if you observe, they were copied from GATE. Okay. Now, if you see this question here, the coefficient of average rolling friction, nothing but the longitudinal friction coefficient is given as FR. Fine. And its grade is G%. The grade is given as G%. The rate of if the grade of the road is doubled, that means it is doubled. Okay, that means 2G%. Okay. What will be the percentage change in the braking distance? Actually, he is asking us to find out the braking distance in terms of the percentage. Like we do know how to. This is a little bit a mathematical kind of, like we need to use some simple mathematics here to find out the braking distance. Okay. Now he is asking us to find out the percentage change in the braking distance. So generally, the formula for finding out this braking distance when we are talking about the stopping set distance when the grade is provided is nothing but VTR plus V square upon 2GF meters into F plus or minus G here, because here the grade is given as G%. Okay, result will be in terms of meters here, where we do know this is lag distance for the braking distance. So now the question is not about the lag distance, it's about the braking distance. Okay, so now we are going to consider only this braking distance, and for that braking distance we need to apply this condition of percentage change. Okay, so initially the coefficient of average rolling friction of a road is FR and its grade is G%. So initially the formula seems to be the braking distance 1 V square upon 2G into F plus G%. Okay, this is positive G because already it was given there, it is positive G. Okay, so this is plus G%. Okay, now the second thing is, if the grade of this road is doubled, okay, so what will be the percentage change in the braking distance if the grade of the road is doubled? So if the grade of the road is doubled, then the braking distance grade of road is doubled, then braking distance road is doubled, then the braking distance can be found out with this formula BD2, nothing but just we need to just double the grade. That's it, very simple. We need to double the grade. Okay, so this is 2GF plus, okay, the grade is double here. Okay, now for these two conditions he is asking us to find out the percentage change. Okay, so percentage change we do know how we have to find it out. Okay, just I'll be calling it as the V1 square. I'll be calling it as no need to take V1 square. Okay, so if the design vehicle to come to stop position measured along the horizontal, all other parameters are kept unchanged. All other parameters are kept unchanged. Okay, the only one parameter that has been changed here is G. So I'm not going to touch any other parameters. Okay, so now we need to find out the percentage change. Find out the percentage change here. So how actually we are going to find out the percentage change here? You can see V square 2G into F plus G. Okay, minus V square upon G into F plus 2G upon V square upon G into F plus C. This is the way that we are going to find out the percentage change, right? This is the way that we are going to find out the percentage change. Okay, now I'm going to solve this question. Okay, I'm just creating more space here. Okay, now just we have to space here. So the percentage change in braking distance can be found out from this simple derivation square upon 2G into F plus G minus V square upon, just writing the same similar thing that I have written earlier, F plus 2G, only the grade is doubled, upon V square upon F plus G. Okay, so this is the percentage change. Okay, so you can see V square upon 2G, V square upon 2G, V square upon 2G, which is common in every thing. Okay, so here only I am remained with 1 upon F plus G, okay, minus 1 upon F plus 2G by 1 upon F plus G. So just I am taking this LCM here. So if you take this LCM here, that comes out to be f plus g, f plus 2g. Okay, just I'm taking this LCM here upon this numerator area. Okay, just have taken the LCM here. So f plus g, f plus g goes out here. So the remaining value is f plus 2 minus f plus 2g, f plus 2g goes, that comes out to be f plus g, okay, upon 1 by f plus g. So this f plus g goes off. Okay, so the remaining thing here remains here, f plus minus f minus g. Okay, so the f also will be going cancelled here upon f plus 2. So here the remaining value is 2g minus g, nothing but g here. Okay, g percentage here. So all the g's were taken, all the g's have to be in terms of percentage. G in terms of percentage, because already in the question you have seen g percentage, right? Okay, so here also I will be taking this as g percentage upon f2 into g percentage. Now that is what nothing but the answer. Okay, g percentage, just I am writing in terms of, I'm just removing the percentage there, 0.01 g upon f plus 0.02 g. So which is we have to check for the option there, 0.01 g upon f plus 0.02 g. So this is the correct answer here. F is nothing but fr. We do know f is nothing but fr. Okay, so everywhere fr will be there. Nothing but f is nothing. I am taking it as fr, rolling friction or longitudinal friction coefficient. Okay, as this have to be expressed in terms of percentage, I am expressing this in terms of percentage. The answer that will be remained here will be 0.01 g upon fr plus 0.02 g into 100. So this is the given question here. You can see from this we will be able to answer this. Simple mathematical calculation, but just we have to know how we are going to find out the percentage change in between two values. So okay, so easily we will be able to solve such a kind of question by doing this simple mathematics without using any calci. We will be able to solve this kind of question because no numerical values are there here. No need to substitute anything. Just we are going to find out the percentage change here, so that by using this simple small derivation kind of thing, solving kind of thing, we will be able to get that answer. Okay, now let us see the next question here. The resistance of the stones against the grinding action under the traffic is measured by. So the resistance, see the question, the resistance of the stones against the grinding action. Grinding action is nothing but attrition which happens in between the aggregates themselves. Okay, whenever load is applied upon aggregates, there will be a grinding property will be occurring in between two aggregates, which leads to the attrition test. That means here that will be checked by something called as attrition test. Okay, so hardness, crushing test, already we have seen all these three different kinds of tests where the hardness test you are going to deal with this impact test, and the crushing strength test you are going to find out this uh, crushing test. Okay, abrasion test we are going to use the Los Angeles abrasion machine. Okay, so here finally the thing that we have to understand here, the grinding action under the traffic is measured by attrition only, because here the rubbing of the aggregates will be happened within themselves when a load is applied upon these aggregates. Okay, so that's why the correct answer for this 18th question is attrition test. Okay, let us see the next question. The maximum number of vehicles observed in a 5-minute period during the peak hour is 150. If the total flow in the peak hour is 1200 vehicles, the 5-minute peak hour factor round off to 2 decimal places is dash. This is also actually a gate question. Similar gate question was there. Similar gate question. Okay. So here he said clearly, like we need to find out the PHF, that is peak hour factor for 5-minute duration. 5-minute duration. So we can take this formula as total traffic upon peak traffic observed, peak traffic of 5 minutes in that hour into number of quarters. So if you simply apply this formula, the total traffic is observed to be here 150. Okay, so 150 upon peak traffic observed in 5-minute duration. The total flow comes out to be 1200 beta. The total flow comes out to be 1200 vehicles. So here I am writing the total traffic as 1200. Okay, fine. The peak traffic observed in any 5-minute duration. So we have to take 5-minute PHF. Okay, so it is 150. So peak traffic observed in a 5-minute duration, this is 150 into number of quarters. So it is a 5-minute PHF. So for an hour, we will be having 12 quarters. That is nothing but 60 by 5. Number of quarters, 12 quarters will be there. Okay, so this value comes out to be 1200 upon 150 into 12. Okay, so this comes out to be 100. 12 hundreds here. Okay, This is 10 upon 15, which comes out to be 0.666 like that. So the correct option here comes out to be 0.67. So the correct option comes out to be 0.67. So very simple question here. He is asking regarding the PHF, that is peak hour factor of 5-minute duration. So just we have to remember that kind of formula so that we will be able to answer this question easily. Okay, generally this PHF is used for the signal designs, peak hour factors. Okay, so this is a very easy way to solve. This is actually a previous gate question. Again, this is also a gate question. Okay, in terms of numerical also, there also in previous gate also the same numerical kind of question was given with the same kind of values. Okay, not exact values, but a little bit changing the values further. But the question seems the resemble same. Okay, so now the next question. Let us observe the next question. Consider the following statements. Here a few statements were given. Running speed is higher than the journey speed. Okay. Journey speed includes delays. Okay. The journey speed is the average speed maintained by the vehicle over a given course when the vehicle is in motion. The running speed is also known as overall travel speed. Now, which of the following statements is correct? Are correct. See here, beta. Running speed is higher than journey speed. Simply remember speed that is maintained only in motion and it doesn't include any delays. Doesn't include delays. It doesn't include any delays. Okay. At the same time, one more speed is there, that is journey speed. This journey speed includes delays. Remember this, it includes delays. That means there will be a delay in the vehicle to move it towards its destination. Okay. So two types of speeds are there here, running speed and journey speed. We have to compare these two in terms of these definitions that were given. Running speed is higher than journey speed. Running speed is higher than journey speed is obviously because in journey speed there will be delay. Okay. If you consider that delay, okay, in terms of the speed, then definitely the journey speed will be having lesser speed because on an average the journey speed will be having lesser velocity when you are comparing with the running velocity. So obviously this statement is correct. Okay, running speed is higher than the journey speed because journey speed includes delays. Very simple. Okay. Yes, the second statement is a direct statement given, that is journey speed includes delays. Fine. Okay. So A and B were correct. Now let us see C and D also so that we will be able to have a clear answer. Journey speed is the average speed maintained by a vehicle. Okay, journey speed is average speed maintained by a vehicle. Fine, good. By a vehicle over a given course while the vehicle is in motion. See here, journey speed in motion. So journey speed generally it includes delays. So we won't consider it. We won't consider this in terms of a motion here because we do know journey speed includes delays. It includes delays. So whenever the delays were coming here, journey speed is the average speed maintained by the vehicle over a given course while the vehicle is in motion. So here the vehicle is considered to be in motion, but the vehicle won't ever be in motion here, beta, because this is journey speed. In addition to this motion, again we will be having delay also. So this statement is not the correct statement. In the fourth option, running speed is also known as overall travel speed. Running speed is also known as overall. Here, no need to take this overall here because running speed, there will be no delay. So this statement is also wrong. So the only statement that is correct here is A and B. Running speed also known as overall travel speed. Running speed, obviously, it will be having here no need to take this overall because there will be no delay at all. Okay. So when there is no delay, then there is no need to take this word called overall. So the correct option will be in between A and B. So running speed is higher than journey speed. Journey speed includes delays. Running speed will be obviously higher than journey speed, as well as journey speeds includes delays. Fine, clear answer. Okay, now let's see the next question here. On a section of highway, the speed density relationship is linear and is given by V is equals to previous gate question. Given by relation V equals to 100 minus 5/6 of K. Fine. Where V is in kmph. Fine. V kmph. Good. K is in vehicles per kilometer. Yes, density will be in terms of vehicles per kilometer only. The capacity of this section of a highway would be dash. Capacity in essence the maximum value. Capacity in essence the maximum value. Nothing but Q max. He is asking to find out the maximum flow. Okay. So the maximum flow can be found out from the simple formula. Q is equals to K max into V max. K max into V max. Okay. Or we can also take it like Kj into VSF upon 4. Kj into VSF upon 4. You can take any relation. The point is here on a section of highway, the speed density relationship is linear and is given by V is equals to 100 minus 5/6 of the K, where V is in kmph and K is in vehicles per kilometer, the capacity of the section of highway. That means here from this equation, we are going to find out the maximum values. From this equation, we are going to find out the maximum values of K as well as V. Okay. So very simple here, for the velocity to be the maximum, the K have to be at its jam density. Remember this, for V to the maximum velocity, for being a maximum speed, the K have to be at its maximum speed. Very simple here. We can also easily understand from a simple example, like when the road is not having any traffic. When the road is not having any traffic, then we can travel with free velocity. That means the maximum velocity. Okay, no traffic, maximum velocity. Simple logic. No traffic, maximum velocity. Okay, so traffic jam. Heavy traffic, the traffic will be jammed. Traffic jam will be observed. Traffic jam. That means here no velocity. That means here no velocity. Here there is no jam. P is having maximum, so no jam. Okay, because no traffic, no jam. Okay, no traffic, no jam. Okay, now we have to just apply this condition to this relation so that we will be able to find out the maximum V as well as the jam density. Okay, traffic jam, in a sense, we will call this traffic jam as Kj. Jam density. Jam density. Okay, so now from this equation, V is equals to 100 minus 5/6 of the K. Okay, now if I take this K as jam density, if I take this K as jam density, that means see here, I'm taking it as jam density. That means here no velocity, velocity is 0. Okay, so velocity will be 0. Okay, when I take this K as K, see here, for K to Kj, for K to be a Kj, be Kj, that means for a density to be the jam density, okay, which implies V have to be 0, because when V is equals to 0, then only we will be able to observe this jam density. Okay, so V is equals to 0, then K comes out to be Kj, 100 minus 5/6 of K, K change to Kj. Okay, now 5/6 of Kj is equals to 100. From this, find out the value of Kj. Kj is equals to 600 by 5, 600 by 5. Okay, so 5 ones 5, 5 2s 10, 120. So Kj is nothing but 120 here. Nothing but Kj will be expressed in terms of vehicles per kilometer. So 120 vehicles per kilometer. Now let us check where the option is given here. 120 vehicles per kilometer. Yes, this is 120 vehicles per kilometer. 60, no, it's not 60. And again, any answers? No, no other answers. Okay, so you can take Kj as 120. Directly, you can take this Kj as 120. Okay. Okay, jam density, right? Yeah. Now I'll be making some free space here, or else we'll do one thing. At this statement only, we can take where is this simple formula? Yeah. So in this equation, we are going to take this V as V max, and V max is equals to 100. Okay. So for V being V max, so I'll be writing like for V being V max, for V to be V max, which implies K is equals to 0. For V, for being its V max, then K will then this value of K will be equals to 0. Then if you take this statement, V max is equals to 100 minus 5/6 of K. Okay, where the K value is 0, then obviously the V max will be equals to 100. V max will be equals to 100. Okay, so we directly got this here. V max we do got 100. So here we can see the free flow speed, nothing but V max is nothing but 100, and the jam density is 120 vehicles per kilometer. You can see here any other options like that? No, no other options were like that given. Okay, so free flow speed is 100 kmph. Okay, and this V max is 100 kmph, as well as the jam density is observed as 120 vehicles per kilometer. So easily we will be able to solve this kind of question from this derivation, from this given equation. Okay, that's good. From this equation, we will be able to find out the V max as well as the jam density easily. Okay, so clear answer, free flow speed will be 100 kmph and the jam density is 120 kmph. Any other answers? Maximum flow 1000, 6000, no. Free flow speed 120, no. Fine. Okay. Now see, the extra widening required for a 3-lane national highway at a horizontal curve of 900 meters radius, considering the wheelbase of 6 meters and the design speed of 100 kmph. So the question is regarding here extra widening, and we do know the formula for extra widening. Extra widening is nothing but mechanical widening plus psychological widening, and we know the formula for mechanical widening as NL square upon 2R, the psychological widening as V by 9.5 root R, where V we can take directly in terms of kmph. Okay, so N is nothing but the number of lanes here, so 3 into 3 lanes for a wheelbase of 6 meters. L is nothing but wheelbase upon 2 plus V. It is given as The speed is given as 100 kmph, so 100 by 9.5 root 900, so that is nothing but 900 NL square upon 2R 100. Okay, so if you solve this, 3 into 36 upon 2 into 900 plus V by 9.5 times of 30. Solve this equation by using simple mathematics, and then you will be able to get the answer directly. If you solve this equation, you need to get like have to get this as 0.06 NL square 6 square 36, fine. And the second thing, 100 divided by 9.5 times 30. So this value comes out to be 0.3508. If you add these 0.06, the value comes out to be 0.410. Value comes out to be 0.141. Fine. This is nothing but your 0.410 will be the correct answer for this question. Okay. So because he is asking the extra widening here, so extra widening will be the combination of mechanical widening plus psychological widening. The formula for mechanical widening is NL square upon 2R plus psychological widening V by 9.5 root R. All the values were given. Just we have to substitute only those values here so that we will be able to get the answer clearly, right? Okay. So if you see the next question here, find out the length of the transition curve for a broad gauge curve of 3 degrees having a cant of 12 centimeters. The maximum permissible speed on the curve is 100 kmph and the allowable cant efficiency is 85 mm. Now he is asking us to find out this length of the transition curve in railways. Okay, so this length of the transition curve in the railways will be found out from the 3 conditions. Likewise, your highways. Okay, the one is from arbitrary gradient. The very first condition is from the arbitrary gradient, where the formula comes out to be 7.2 times of E. Okay. The second is based on rate of cant efficiency, or based upon the cant efficiency. Okay, so 0.073 into D into max. This is the formula for length of the transition curve based upon this cant efficiency. The third, rate of change in super elevation. So based on super elevation, based on rate of super elevation. Okay, so this super elevation, the formula comes out to be 0.073 times E into max. Okay, so all these were length of the transition curves, and we have to choose the maximum answer of these three. We have to choose the highest of these three. Okay, highest of all these 3 terms, so that it will be getting in terms of your answer. Okay, so the very first option, the very first condition, 7.2 terms of E, where the value of E here, the cant of 12 centimeters are provided. E will be in terms of centimeters here, in centimeters, remember. D will be in centimeters, remember, and V max will be in kmph, and the resultant you will be getting in terms of meter. Okay, so 7.2 terms of 12, this is the very first condition, and the second condition comes out to be 0.073 into the what we call cant efficiency is given as 85, that is nothing but 8.5, which we have to take in terms of centimeters. This mm we have to take in terms of centimeters, multiplies by V max, where the maximum permissible speed on the curve is 100 kmph. So 100, this is the second condition. So the third condition comes out to be 0.073 into E, that the cant of 12 centimeters into V max, again 100. Okay, solve this by using simple mathematics so that you will be able to get the answer directly. So if you solve this, 7.2 times of 12, the answer comes out to be 86.4. Okay, so that is also there in the options. And if you see the next thing here, 0.073 into 8.5 into 100, the value comes out to be 62.05. 62.05, yes, that is also there in the options, near the option. Okay, and if you see here, this is 12, the answer comes out to be 87.6. Okay, so that is also there in the options, 87.6. But we have to choose the highest of all these three. So Of all these three values, 87.6 is the correct answer. So obviously the correct answer is 87.6, not these options. You can see here all the options were given, but see, all these were wrong. Okay, the only correct answer here is 87.60 will be the correct answer. Okay, requires a little bit problem solving here. The design speed of a road, the next question, the design speed of a road is 72 kmph, assuming the driver reaction time as 2 seconds and the coefficient of friction of the pavement surface as 0.30, the required stopping distance for a two-lane, two-way traffic is dash. Okay, simple direct question. We need to find out from this stopping side distance formula, which comes out to be VTR lag distance plus V square upon 2GF, which we do call it as braking distance. Okay, the resultant will be in terms of meters. Okay, so where we have to take in terms of meter per second, but here it was given in terms of kmph, so just we have to convert this 0.278 into velocity 72 into reaction to TR plus 0.278 into velocity 72 whole square upon 2 into 9.81 into friction coefficient. Friction coefficient comes out to be 0.30, 0.30. Okay, and now we have to solve this to get the answer correctly. If you solve this, the answer comes out to be, if you solve this, the answer comes out to be 106.67. 106.67. If you solve this, the answer comes out to be 106.67 meters. Now let us see the next question. A vehicle has a wheelbase of 6 meters. What is the off tracking in meters while negotiating a curved path with a mean radius of 60 meters? Okay, so the question is regarding here the off tracking here. Okay, now what is this off tracking? Off tracking is nothing but the vehicle coming off the track, okay, from a single lane. Okay, so generally we do know this extra widening, the extra widening is equals to, that is we do know the extra widening is equals to mechanical widening plus psychological widening, right? Okay, but when we talk about this off tracking, we are not concerned this, that means we won't find out this psychological widening. We will be taking care of only this mechanical widening. And the formula for mechanical widening, we do know NL square upon 2R, but here the off tracking will occur only from a single, that means only from a single lane. So that's why the value of N comes out to be 1 here. So finally the off tracking will be measured by a formula called L square upon 2R. Actually this is not any formula kind of thing, but a simple Pythagoras theorem will be applied here. Okay, from that we need to find out this off tracking. So L is nothing but the length of the wheelbase, where we are going to find out 6 square upon 2 into the radius which is given as 60 meters. Okay, nothing but 36 upon 120. So the answer comes out to be here 36 upon 120. The answer comes out to be 0.3. So the correct answer is 0.30. Okay, so the answer comes out to be 0.30. Okay, so very simple question. Here we will be able to easily find out, but we have to know what is off tracking is. Off tracking is nothing but when a vehicle off tracks, that means gets off outside the track. Obviously this getting outside the track will be occurring only from a single lane. So that's why we will be taking this N as number 1. So that's what the formula comes out to be, L square upon 2R. Okay, now let us see the next question. So see the next question. While aligning the hill road with a rolling gradient of 7%, a horizontal curve of radius 100 meters is encountered. What is the compensated gradient in the percentage as per IRC? Now the question is regarding the compensated gradient. Compensated gradient. It's not about the grade compensation, it's about compensated gradient. Okay. Now we are supposed to find out this compensated gradient because the question is very clear about that. Okay. So now what is this compensated gradient? When we are traveling upon a hill kind of structure, that means whenever there is a road observed upon an hilly structure, you will be able to observe like this. The roads are built here like this. Okay, now what is happening here on the turnings? Here we will be able to observe a horizontal curve from, if you observe from the top view. At the same time, we will be able to observe there is some gradient here, right? So two things are coming into the picture here. That means a gradient is coming as well as a horizontal curve is observed. So on this area, as the vehicles will be having difficulty to negotiate this kind of curve, here we need to provide something called as grade compensation. That means we are not giving the gradient as per the design. Okay, we need to compensate it. We are going to reduce the value. Okay, which we are going to technically call it as grade compensation. Grade compensation. Okay, now after finding out this grade compensation, we are supposed to find out this compensated gradient, like with what value the gradient got compensated. That's what the final thing that we are going to find out here. Okay, so how are we going to find out this grade compensation? grade compensation will be founded from a simple formula. Okay, so 30 plus R upon R or 75 by R or 75 by R. We have to choose the minimum of these two values as the grade compensation. Okay, so simple, we need to use this radius here. So 30 plus radius comes out to be 100 upon 100. This is one formula, and at the same time 75 by 100. This is one formula. So this value 75 by 100 comes out to be 0.75, and here the value comes out to be 130 upon 100, right? 100 plus 30, 130 upon 100. The value comes out to be 1.3. So we have to choose the minimum value here. The minimum value comes out to be 0.75. So the least value is 0.75. So the grade compensation have to be opted as 0.75, and from here we are going to find out the compensated gradient. Compensated gradient. The formula comes out to be provided gradient minus grade compensation, or given gradient minus grade compensation. So the given gradient, if you observe here, 7% of the gradient was given while aligning a hill road with a rolling gradient of 7% minus a horizontal curve of radius 100 meters is encountered. What is the compensated gradient? So this comes out to be 7% minus grade compensation. We got this is in terms of percentage. Actually, these formulas will be in terms of percentage. So this is 1.3% and this is 0.75%. Okay, so 7 minus 0.75, this comes out to be 6.25, right? 6.25 plus 0.75 comes out to be 7. So 6.25 is the correct answer. Okay, so very simple question. We will be able to find out the answer from this kind of formulas if you know it. Okay, so the next question. The linear relationship is observed between speed and density on a certain section of a highway. The free flow speed is observed to be 100 kmph and the jam density is estimated to be 120 vehicles per kilometer length. Fine. Based upon the above relationship, the maximum flow expected on this section and the speed at the maximum flow will be respectively dash. The simple thing here, a linear relationship is observed between speed and density. Yes, we do know a linear relation will be observed in between speed and density. Okay, Q is equals to K into V. On a certain section of a highway, the free flow speed is observed to be 100 kmph. Fine, this is 100 kmph free flow speed, and the jam density is observed Kj. The jam density is observed to be 120 vehicles per kilometer. Okay, fine. Based upon the above relationship, the maximum flow Q max is observed to be Vf into Kj upon 4. Okay, the question is based upon the above relationship, the maximum flow expected on this section. The maximum flow expected on this section 100 into 120 upon 4. This value comes out to be 12000 upon 4. 4 3 is 12, 3000. Okay, 3000. This is Q max, that is vehicles. Q max, that is flow, vehicles per hour. Okay, and now the question is based on the above relationship, the maximum flow. We found out the maximum flow here. The flow can be easily found out from this relation. Q max is equals to Vf into Kj upon 4. On this section, the speed at the maximum flow will be dash. Speed at the maximum flow V at VSF. Excuse me. Okay, so V can be found out, that is, or the speed can be found out, the half of the speed given velocity, the free flow speed, sorry, V is equals to VSF upon 2. This value comes out to be, it is 100 kmph. Speed is given as 100 kmph, right? 100 kmph. Okay, upon 2, this comes out to be 50 kmph. So 3050 kmph is the correct answer. 3000 vehicles per hour and 50 kmph is the correct answer. Very easy and simple. Okay, if you observe the next question here, the average spacing between the vehicles in a traffic stream is 20 meters and the density of a vehicle, density in vehicles per kilometer of the stream is dash. Okay, so here he gave the average spacing. Average spacing was given as 20 meters. Average spacing was given as 20 meters, and what's the next thing he said? Then the density in vehicles per kilometer. Then the density in vehicles per kilometer is dash. Very simple and easy equation. Okay, nothing but the spacing is given here, and we do know the spacing. Okay, the spacing between two different vehicles. Okay, we can take it as from the formula also 0.7 VB plus 6 or 0.2 VB plus 6. But here Taking that formula is not necessary because the density is found out in terms of vehicles per kilometer. Nothing but for a kilometer of distance, how many vehicles are going to get accommodated. So this is 1,000 meters, kilometers nothing but 1,000 meters upon 20 meters is nothing but the spacing here. Okay, so 0, 0, this comes out to be 50. So it comes out to be 50 here. So 50 is the correct answer. Very easy and direct question was given here, right? And if you see the next question, match the following was given with the different signs. Yes, we do know all these kinds of signs. This is cautionary, CAUTIONARY, cautionary signs, okay, indicatory signs or indication signs, fine signs, as well as yield sign, prohibitory sign, stop sign. So these are the signs that are given here and we need to match with the following options. We need to match with the following options. Okay. So we do know stop sign is an octagonal sign because this is an exception in the case of these mandatory signs, mandatory or regulatory signs. Okay. Cautionary or warning signs, both are same, we do know. Indicatory signs generally represented with a rectangular shape. Then generally these indicatory signs are nothing but what we call informatory signs. So generally these are shown with a rectangular shape. Okay, yield sign. So this is a kind of, this is also a kind of exception which we do observe with this kind of shape. Okay, then nothing but a triangular shape that is formed. This is also a mandatory or regulatory. Actually, this is a mandatory or regulatory sign. That means we have to must follow it. Okay, so this is a yield sign. So prohibitory sign. This is also nothing but mandatory prohibitory sign. Now, if you observe here, if you choose the options from these kinds of areas, like whatever the answers that are given here, that is octagonal, rectangular, warning or informatory, these are shown in triangular shape. These are shown in triangular shape with triangle apex upwards. Here the triangle shape will be downwards. Okay, prohibitory or mandatory or regulatory signs, they are shown with a circular shape. Okay, now simply match all these here. So the cautionary signs are nothing but warning signs. They are shown in triangular shape. Upward equilateral triangle. So you can see here upward equilateral triangle. Indicatory signs rectangular shape. We can see this is rectangular shape. Prohibitory signs circular shape. Prohibitory or mandatory or regulatory this prohibitory can also be read like mandatory or regulatory signs. All these are same. Okay, so that is a circular shape. Stop sign, this is an octagonal shape. Okay, so you can simply match this. A comes out to be 3, only one option. A comes out to be 3, B comes out to be 4, yes, B comes out to be 4, C comes out to be 1. See, yield sign, yes, download, we haven't seen this. Yield sign, I have already written here. Download equilateral triangular shape. Okay, and D comes out to be 5, D comes out to be 5, yes, D comes out to be 5, and E comes out to be 2, E comes out to be 2. That is octagonal. Okay, just we have to have an idea upon these signs so that we will be easily able to answer this question. A road is being designed for a speed of 100 km/h on a horizontal curve with a super elevation of 0.7%. If the coefficient of side friction is 0.15, the minimum radius of the curve required for the safe vehicular movement is dash. So this question is about the super elevation, and we do know how actually we have to find when this questions are given upon the super elevation. E plus F is equals to V square upon GR. Okay, but he is asking us to find out the value of R here. So GR is equals to V square upon E plus F, and if I send this G here, the G comes out to be here. Okay, so the radius, that's what the question he is asking here. We need to find out this 0.278 into velocity is given as 100 km/h, 100 whole square upon E, super elevation value 0.07 plus F, friction coefficient, side friction 0.15 into G 9.81. So if you solve this, we will be easily able to get that answer. Do that simple mathematics. Of course, it do require some mathematical work which we have to carry out with calci kind of thing. Okay, so if you observe 0.278 multiplies by 100 whole square, the value comes out to be 778. 778.84 upon answer divided by 0.07 plus 0.15 into 9.81. The value directly comes out to be, the direct calculation value comes out to be 358.094. 358.094. Nothing but the value comes out to be 358 here. Okay, you can take directly. That means we have to know this simple relation so that we will be able to answer. Okay, this do require some kind of calci work, but mathematically also we will be able to solve this, but it takes some time. Okay, so this is a kind of question. So these are all the questions in the area of transportation engineering which we got for this AW exam. Okay, so all the questions we have seen clearly. Okay, so only the thing is that we have to have the basic knowledge. It is not like the toughest kind of exam. The toughest kind of questions were given. The questions were easy, but the thing is a few questions require more calculation point, which takes some time here for solving or for getting the answer exactly, because here you can see the values were given up to 1 decimal places, so that we have to calculate more more precise. Okay, so these are all about the questions in the area of transportation engineering. Thank you.